Hello, yeah, hi everyone. So to the participants, we are just waiting for 2 or 3 more minutes for other participants to join, and we are waiting for our speaker as well to just make the setup perfect. And we will be starting shortly. Thank you. Hello everyone. Steve, sir, could you please confirm if you are able to hear us?
I can hear you loud and clear.
All right, perfect. Akriti, you can start now.
Okay, ma'am. Any sufficiently advanced technology is indistinguishable from magic. Embracing the need of the modern industry and reciprocating it with the strength of technology, I, Akriti Bhan, member of IEEE YMCA student branch, would like to extend warm greetings to everyone present here. We are extremely honored to host the fourth event in our mega membership awareness program, IEEE Drive 2021 in collaboration with IEEE Region 10 and IEEE Delhi section, which aims to increase awareness about IEEE and its diverse benefits. We welcome all the individuals present in this meeting on the virtual tour to the Atlas experiment at CERN. In the times of today, where everything has developed into the virtual realm, it becomes extremely difficult to navigate through the various available online sources and find a credible source of information for one's field of interest. This event of our IEEE Drive focuses on enriching the audience members with the knowledge of the research field and vast scope in the domain. We are grateful to have you all along with us today. CERN is one of the world's largest and most respected centers for scientific research. ATLAS is the largest general purpose particle detector experiment at the Large Hadron Collider, a particle accelerator at CERN in Switzerland. This session is focused on providing the audience with a glimpse of the workings and the world at a research center which is completely engaged in developing resources for a greater humanity. We hope this session will give you an extremely valuable insight into this area of industry and its importance. As the beginning of any auspicious event is marked by seeking the blessings of Goddess Saraswati and following the customs, we will begin this event with Saraswati Vandana. For further proceedings, I would like to hand over the virtual stage to the tech team.
कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः
Thank you, technical team. Now, I would like to introduce the speaker who will be guiding us through the journey of the virtual visit, Dr. Stephen Goldfarb. Sir is a physicist at the University of Melbourne and researcher at the Atlas experiment. He received a Bachelor of Science in Mathematics from the University of Michigan and a PhD in physics in 1991 for his work on the L3 experiment at CERN. He is a webmaster for the Atlas public web pages, chair of the International Particle Physics Outreach Group, on-site coordinator of the REU Summer Student and Research Semester Abroad programs for American undergraduates at CERN. Sir also has various projects under his belt. The entire team at IEEE YMCA student branch is extremely delighted to have such an amazing and inspiring individual as a speaker for our event. Thank you so much, sir, for gracing us with your presence. Now, I would like to.
I'm sorry, go ahead.
Now, I would like to invite the convener for this event, Rashmi Agarwal ma'am, the secretary at IEEE Women in Engineering Affinity Group Delhi section, and Execom member at IEEE Delhi section, and the branch counselor at IEEE YMCA student branch to deliver a welcome note for our speaker and all the participants. Over to you, ma'am.
Thank you, Akriti. Thank you, everyone. Good afternoon, everyone. So I am so glad that Professor Stephen has accepted our invitation of organizing this virtual visit. I am really thankful. Today, I would like to welcome the esteemed speaker of virtual visit to Atlas, CERN, Professor Stephen Goldfield, a physicist of the University of Melbourne, researcher at Atlas University. I, sir, really thank you for accepting our invitation and sparing time from your busy schedule to allow us to host you. Sir, as all the participants know that this is a virtual visit to Atlas CERN, which is an event under IEEE Drive 2021 in collaboration with IEEE Delhi Section and Region 10. So I welcome all the participants. Sir, I hope all the participants will have a great knowledge after visiting this virtual visit to CERN. Thanks a lot. I again welcome you to all the splendid virtual visit. Thanks a lot.
Thank you, ma'am, for these words. Without taking much of your time, I would now hand over the virtual podium to our speaker for today's visit, Dr. Stephen Goldfarb, for the official commencement of the learning part of the session. Over to you, sir.
Well, thank you very much for that very kind introduction. And also thank you to everybody for joining. I'm very happy to know that there are so many people who want to be here and to learn more about what's going on in fundamental research here at CERN. It's a very important thing, as you already mentioned, actually, at the very beginning of this, understanding where knowledge comes from for humanity is really important, especially these days. And I think it's good to see the effort that goes into creating our understanding of our universe. Now, I'm not sure if am I sending you video? Can you see video yet? I don't, normally I should be able to see my video.
Oh, yes, sir. It's fine. Perfect.
It's good. You can see all right?
Yeah.
Oh, okay. I won't be able to see it then. I'm going to make it horizontal and hope I'm pointing in the right direction. It would be good if I could actually see what I'm showing you. Is there any way, maybe if the sharing was stopped, then I could see the video that I'm showing you.
All right.
There. That's right. Okay, you just see me. How uninteresting. That's me. It's good that you showed me this. Now I'm going to turn you around and show you where you're at and tell you a little bit about that. Okay, so this is where I'm at. This is one experiment at CERN. CERN is the European Laboratory for Particle Physics. Our goal, the entire goal of the laboratory, all of its experiments, is very basic. It's to understand what are the fundamental components of nature, what are the building blocks of our universe, and what are the rules around those building blocks that give us the wonderful world that we live in. So all of the experiments are designed to do that. We all do it in different ways. ATLAS is one of 4 experiments on the Large Hadron Collider. That's a 27-kilometer round ring, which accelerates protons in opposite directions and causes those beams to pass through each other at the points where we put our experiments. So this is one of those points. We call this LHC 0.1. I've come from way up there. That's almost 100 meters from the very top. You can actually see the roof of the building that's above our access shaft. And we have 2 of these access shafts. And goes all the way down to the bottom down there. That's our detector in the middle, and that's at the point where the particles pass through each other. Now, I should mention, let me just turn this around so I can talk to you here. I should mention to you that there are many here at CERN. Collider is not the only show in town, but it is the highest energy collider in the world these days that we've made, that humans have made. Mother Nature has done much better. Mother Nature collides high energy charged particles in space, in our upper atmosphere. In fact, over the course of time since the birth of our sun, the LHC, which we're doing here, has been done about roughly, it's an estimate, 10,000 times already. So whenever somebody asks, how are you sure that it's safe? Well, Mother Nature has done this experiment. It's safe. The energies that we talk about very human beings, they're roughly the energy of a fly, the collisions that we make. So, however, what's very interesting about that is that we take that energy, which seems small, and we squeeze it into a very, very, very tiny point. And that means you can produce particles which are more massive, more energetic than anything ever studied before. And that's what we do here down below me at ATLAS. Now, let me give you a brief introduction of what goes on at CERN and the LHC, what we're looking for. And then I'm going to spend more time, I hope, answering your questions. Really come up with good questions. I'll do my best to answer them. I'm a scientist, so if I don't know the answer, I'll just tell you I don't know the answer. That's somebody else. We're happy to say, I don't know. Now, across the street from the Large Hadron Collider is where the main campus is of CERN. And over there, there are a lot of other fantastic experiments. And these experiments include studies of antimatter. Antimatter is matter, only with the opposite charge. It's something that was produced at the beginning of our universe, 13.8 billion years ago. I believe that. I might be old, but I wasn't around back then, but I understand. Roughly 13.8 billion years ago, at the Big Bang, the universe produced equal amounts of matter and antimatter. This is what we see in all of the collisions that we measure. In every experiment we've seen, we produce equal amounts of matter and antimatter. The strange thing is that while that happened at the Big Bang, all that was produced and all of the antimatter ran into the matter. And when matter and antimatter run into each other, they annihilate and give you energy. Everything disappeared. We only had energy left. But the very strange thing that we do not understand is why we're here. Why did some dust remain after all of this? And that's a big question. It's a human question. Why do we exist? And we're still trying to understand it. That's only one of our big questions that we're trying to address. And there's a whole antimatter decelerator, it's called. It is very difficult to create antimatter and then to slow it down and to be able to study it. But they are understand the differences. That's one big thing that happens across the street. Another important thing that happens across the street is we have an isotope producing machine called ISOL. Isotopes, as you might know, are used in medical physics or in medicine. Studying different isotopes can help us to find solutions, ways to treat different diseases, and also even to try to determine where the diseases came from. So it's very, very important. It's used quite a bit. There's a large facility over there that does that. And we also have something that's a prototype detector for studying neutrinos. Neutrinos are a particle which is fascinating. They pass through everything without interacting, unless there's a lot of material. There's some neutrino detectors around the world, in Japan, in the South Pole. Pretty cool to work on something like that. It's an experiment called Ice Cube. It actually uses a huge block of ice, which happened to be there because it's the South Pole. And they put detectors all through it to look for interactions of neutrinos, neutrinos that either came from above, or more likely, what's interesting is neutrinos that came through the entire planet and interacted there. So they studied this. They studied this in Japan at Super Kamiokan. It's amazing because only recently they discovered that neutrinos, these particles which hardly interact with anything, have a mass. That was a very important discovery. A very interesting particle because they can change back and forth from one type to another. We, with our experiments, don't actually see neutrinos. They pass right through it. But because we built our experiments all the way around the collision point, we can tell when something went through that we didn't see. I know it sounds strange, but there's this thing called conservation of momentum, which allows us to tell when something goes through that we didn't see. That's important for testing the theory, the standard model. That's our theory that's been working since the 1960s. And checking to see if we see the sort of missing energy on occasion that we expect, but also for exploring in case maybe there's something else out there that has a large amount of missing energy and that we've never detected before. And there's a really good chance of that. This is another really big question we have. There are some brilliant physicists, astronomers, actually. A guy named Zwicky was one of the first to notice that there was something strange when his telescope looked at clusters of galaxies, that the motion of the galaxies was too fast to the amount of matter that you could see. He said, there's something in there. I don't know what it is. I'll just call it dark matter until we figure it out. And then Vera Rubin, another brilliant astronomer, measured, when she got better devices, measured the spinning of stars within a galaxy and was able to determine, like Zwicky actually, that roughly 80 to 90% of the stuff in a galaxy is stuff we don't see. It's not the stars, but there's something in there. Many other measurements have happened since then. And as far as we can tell, there is dark matter, maybe not a good name. I would call it invisible matter myself, scattered all about our universe. And it's most of the matter in our universe. So when a physicist tells you, hey, we have this brilliant model, it explains a whole lot. We know what the fundamental, the elementary particles are and how they interact. You can remind them that they only know roughly 15% of matter. And that's not all. What we're missing, even more than that, is an explanation of why this universe, which, as I mentioned, started 13.8 billion years ago when I was just a child, is expanding at a faster and faster rate. We don't get that at all. It would make sense that the gravity that holds stars together in galaxies, for example, holds our planets around our own star, the sun. It would make sense for the expansion of the universe to be slowing down. But instead, it's accelerating. It's getting faster and faster. We don't get that. We calculated the amount of energy it would take for that to happen. And that's the majority of the universe. Roughly 2/3 of our universe is this energy that's causing its expansion. And we call that dark energy because we don't have a clue what it is either. So we're living right now in the dark ages. We understand perhaps 5% of our universe. The rest we don't understand. Yet, to defend, learning to know is 5% of the universe. It was a huge battle and a very important one. So now it's just a question of trying to figure out what these other things are. Those are just some of the questions that we're trying to figure out here, but we have a lot more, and I hope that you're going to have questions as well. Now, I've explained to you what's across the street over here. So I'm going to turn this around again. I'm going to point you in directions you're not going to see the things I'm going to tell you about. Actually, through that wall, I am standing directly over, I can show you this way. I'm directly over the Large Hadron Collider. It would pass underneath my feet there, and it would go right into our detector there in this direction. And from the other direction as well, it would come to the center, and that's where the collisions happen. I'm going to take you down there. If you're patient with me, I'm going to just do a little more explanation, and then I'm going to walk you downstairs and show you some even better views of our detector. So what's interesting, what I was going to tell you about is that if you went all the way through there, you followed the LHC that way, where there's a C, you went all the way around there, you would find another detector at another collision point that's called ALICE. ALICE is a detector that's designed to look at the collisions of heavy ions. We take lead atoms, strip all of the electrons off, and then we pass them through each other. We do that sometimes during the year. Most of the time, we're passing protons through each other. But sometimes we do it with heavy ions. And their detector over there is designed to look at that, to try to understand our primordial universe. When quarks and gluons, the things that make up protons, were living together in a kind of soup. It was before protons were born. Okay, so that's very early universe. Let's say a microsecond or so, up to a second of the universe. Most of the great stuff that happened after the Big Bang happened within the first second, amazingly enough. So that would get you to ALICE. If I were to go the other way through this wall here and go down the tunnel that way, I would end up at an experiment called LHCb. LHCb is specifically designed to try to understand this imbalance of matter and antimatter. Why do we exist? Why was there a little bit of matter left over after all of the collisions? There are some hints that certain particles will decay more to matter than antimatter, but those do not provide enough of a difference to explain why we exist. Finally, I should mention our really good friends who are across the way there. So they're all the way on the other side of the ring. So if I were to walk all the way around the ring and get exactly to where we're at here, I would see our friends at CMS. That's another enormous detector like ATLAS, which is multi-purpose, designed to explore. And they, much like ATLAS, we do very similar physics, although our detectors really look completely differently. They have a very similar capabilities. CMS is stronger at some types of physics, and Atlas is stronger at some other types of physics, so we're very complementary. And we often work together. Once we've made a discovery, we check with the other to see that they've seen it, and then we combine our data. So that's how things work. We have a sort of a co-opetition, I call it, where we compete with each other while we're doing measurements, because you do not want to see the other experiment's results before you've done your work in order to say non-biased. But then afterwards, we compare our methods, we compare our results, and we will often combine them to get the best possible measurements that we can. So as an example, Atlas and CMS over there, we're the two experiments that discovered the Higgs boson in 2012. And we both made that discovery at the same time. We could check with each other, and that really confirmed the fact that it exists. And we've been spending a lot of effort measuring that particle and learning all of its properties since that time. So that sort of explains what goes on here. Let me tell you one other thing about the LHC, and then I'm going to take you on a walk around. One thing that's interesting about it is most people call this a collider experiment, that we're colliding protons together. Technically, that's true. They do, run into each other, but it's not a simple thing, and I'll explain why. In the beam, which goes underneath here, it's not just a continuous beam of particles. It's actually bunches. There are bunches of protons. Now, we use protons because they're charged particles, and you can accelerate charged particles with a magnetic field and an electric field. You can't do that with neutral particles like a photon or a neutron. You have to have charged particles to be able to squeeze a beam, to make it turn around, and to accelerate it, to give it a little kick. We use an electric field to give it a kick, like a mother would push a merry-go-round. As these particles go around here, we give them a little kick at one point, and they go faster and faster to get up to the high energy that we want to produce the types of physics that we want. So we use these charged bunches. They're in bunches because you need time for your detector to be able to make a measurement and then move on to the next one. So we give our detectors lots of time, 25 nanoseconds. They get between the crossing of the bunches. That's enough time that the detector can sort of recuperate and make the next measurement. So these bunches, a bunch sounds like a little bit, got a little sack full of protons. One bunch of protons in the Large Hadron Collider is 100 billion protons. So that's a galaxy of protons. Andromeda, the Milky Way, they each have roughly 100 billion stars. I never counted them all myself, but something like that. That's a good estimate. That's how many protons we have in the bunches. Now, when the Milky Way and Andromeda run through each other, and don't panic, you still have time, like a billion years or so, okay? So you're going to be quite old when this happens. When these two galaxies pass through each other, the number of stars that are actually going to hit each other is approximately 0, okay? That's because even though when you look at these galaxies, they look like they're dense bunches of stars, space is vast. There is a lot of space between stars. Even in our own solar system, there's a huge amount of space out there. You can actually take all of our planets, including the huge ones, Jupiter, Saturn, Neptune. You can take all of them and place them between the Earth and the moon. That gives you a better concept in mind. Most of us don't think of it like that. We think of the moon as a little thing that's just orbiting around the Earth closely. It's not. It's far away. And most of space is like that. There's a lot of nothing out there. And that's true inside us as well. There is a lot of nothing inside a proton. So even when we squeeze the beam as tight as we possibly can and get protons to pass through each other. So when we take 100 billion protons against 100 billion protons in the LHC in the last run, we got roughly 50 or 60 that would actually pass through each other. But even when we managed to do that, most of the time, the parts of the protons, quarks and gluons that you really want to interact, those are the elementary particles, miss each other. So most of the time, we're not seeing anything that's interesting. We're just seeing charged particles scattering off each other, something which we understand already. That means that for a detector like this, we need to have a system set up so that we take a picture whenever there is something interesting that happens. Whenever the components of the protons, whenever the quarks or the gluons, which hold them together, those are force particles, gluons, when they really have an interaction that does something interesting, we take a picture then. We do that through a system we call the trigger system. That's the idea, is you use a trigger to take a picture, say, okay, I want to keep that. The trigger system works very fast, on the order of nanosecond precision, in order that we can keep all the data that's interesting. And to choose that is very difficult. It's very complex. We know what types of things to look for, a certain amount of energy, certain particles, a single electron or photons or muons, certain things that we expect to come out. But we also have to trigger on things which we don't necessarily know if they're going to exist, things that theorists have told us that we should look for. So that's the type of, that's way a device like this works. Now, what I'm going to do now is I'm going to take you on a brief walk. We're going to go down the steps you're going to go down the steps with me here. We're at the very top up here. You can see the whole cavern here. What we're going to do is we're going to go down and get up close to the far end of the detector. And that's the muon system. I know it very well because I worked on that when I first started to work on Atlas. And that was around 1998. So before some of you were born, perhaps. I started to work on this, and I coordinated the development of the software for this system. But I'm also going to show it to you, not just because it's my favorite part, but because it's one of the only parts we can really get up close and personal with on the detector, because it's right here at the very end. So you can see the very top of it here. You see these very long tubes. There's a lot of services. I should say, one of the most fascinating parts of all of these experiments is the fact that we didn't build these in one laboratory or in one institution. We needed the resources, the human resources, the human input, and also, of course, monetary resources of many, many, many different countries, many different people. There are more than 5,000 people who worked on this experiment, who helped to do all of this work. Every single one of these little wires in here, every single connector required effort. And this is all given by the many, many, many people who worked on the experiment. Like I said, more than 5,000 have worked on this. What I want to show you here, I can just show you a little part of the detector here. You can see connectors, you can see these tubes. What's interesting about this is it gives you a good concept of how a detector works. Inside each of these tubes, these are very long tubes, by the way, 6 meters long at the very far end here. Inside each of these tubes, there's a wire, goes right down the middle of it. And in between the tube and the wire, there's a gas. In this case, we use argon CO2. That's a gas which, if a charged particle passes through it, will ionize. That means an electron could get knocked off of the gas. Now, that's interesting to us because we would like to capture that electron and know where a particle passed through the detector. And so what we do is we put a high voltage between the tube and the wire. The wire is positive voltage. And so when the electron gets knocked off the gas, it goes to the wire and it goes zoom to the far end. where there's electronics, which will grab that charge signal, amplify it, and send it out to our counting room where we have electronics which can make measurements. So that happens in each of these tubes. If a charged particle comes out to here, goes through these tubes, we know from timing information at what radius of each of these tubes the particle passed through. And we can then get all these little circles there and reconstruct a track. That track is, if it came all the way out to here, is of a muon. A muon is simply an electron, but more massive. That's what can make it out here. Muons are great for making discovery and for making measurements because they are elementary particles. By the way, elementary, I'm going to say that many times here, elementary particles are what we're trying to understand. Elementary particles mean they're points in space. They have no structure. They have no volume to them. They're not made up of anything, right? Like I said, we're trying to find the Lego bricks of our universe, the basic building blocks of nature. And we believe muons to be that. Now, what's fascinating about them, which puzzled us for a long time, was that a muon is an electron, but with more mass. And we were puzzled by that because it didn't make sense for, mass. What we're used to in mass is that it represents structure, represents some volume. Usually something has to have a volume in the energy, like binding energy. You learned in chemistry about binding energy. The binding energy of a molecule or even of an atom is what gives it mass. But in this case, it turns out that elementary particles have an intrinsic property called mass. And I'll tell you a little bit more about that later. That was what was important about discovering the Higgs boson. But in the meantime, just to finish this story here, we know if a particle went through here. Now, the other important thing to know, so there's one concept that you need to know to build a detector is ionization. Out here, it's done with tubes and wires. In the middle of the detector, which I'd love to take you to the middle of the detector, but I can't get in there. In the middle of the detector, next to where the collisions happen, we have silicon detectors. Silicon also ionizes. And so you can etch detectors onto a chip and you can actually, excuse me, you can then measure very precisely charged particles that came from the collision. So that's what happens inside there. It happens out here. We measure these charged particles. Now, the other concept you need to know to build an accelerator and to build detectors is that a charged particle in a magnetic field will curve. So if you surround the charged particle in a magnetic field, then you'll see it curve. The stronger the magnetic field, the more it will curve. The more energetic the particle, the less it will curve. So if you really want to measure energetic particles, which are what come from massive particles produced in the center, then you need a big detector and very strong magnets. Now I'll show you the magnets as we go around. I'm going to take you down and show you the magnets that we use here. So those are the two concepts. If you know those two concepts, you can go home, get a few $billion and build yourself a detector and an accelerator. Okay, I don't think you can order it on IKEA, but do the best you can. Okay, so this is the outer part of the detector. I'm going to take you downstairs, get you up close. I'll tell you a few more things, and then I want to spend time answering all of your good questions because I'm sure you have some really good questions here. I'm going to take you. You can see actually there's an elevator inside a detector. That's how big this thing is. I'm going to go down to level 6. And there I have a little walkway. I'm going to take you on a walkway so you can actually see a little bit more. Here's these beautiful tubes. By the way, part of this that's very interesting, you see these little devices in here are used to align the detector. When we put everything together, we align it as close as we can to where we want it to be within millimeters. But we then use measurements continually. We're taking measurements of this whole device here in order to align it to a precision of tens of microns. So that's like your hair. If you hold one of your hairs out, we can tell you if a muon passed above that hair or below that hair. That's the precision that we need to reach out here with these devices, which are enormous. The diameter of this wheel here is something like 25 or 26 meters, depending how you measure it. So it's a very, very, very large device to have lined up as precisely as you possibly can. So I'm just walking over the LHC here. I want to invite all of you, when you can, to come here in person to visit. But I should tell you that even visitors who come here in person don't get to have a tour like this, where you get to go all the way around and see everything. I'm really happy to do this with you because I get to go see everything. And I should also tell you that whenever I come down here, I'm taking pictures. And I've been down here thousands of times now. So this is what I want to show you. This is our beautiful detector. On this side, from here on, all the way back there, going down half of a football pitch. I don't know what size that is in terms of cricket, but it's big. You go all the way down there, you go about 46 meters from one end down there, all the way down to there. That's the length of the detector. This thing in the center here is our end cap toroidal magnet. So it's a magnet. It makes a magnetic field that goes in a loop. On the barrel part, these big tubes you see right here, that's part of the barrel toroidal magnet that goes all the way, that tube goes all the way there and does another loop. And that makes a magnetic field that goes around in a loop like that. That's the unique property of the Atlas experiment. No other experiment has anything like that. Most experiments have only a solenoid. You guys made solenoids in school, right? You took a wire and you curled it around. You could take a pencil and wrap it around that and put a current through that coil, and you get a magnetic field that goes like this. And that's the easiest thing to do. And in the very center of our detector, we have a solenoid like that. However, if you have an enormous detector and you have a solenoid, Mother Nature won't let you just have a simple magnetic field that goes like this. It has to come back. The field has to go and has to wrap and come back through some material. So you have to have a lot of material in your detector. Now CMS, they went that direction. And if you look at the tracks from the detector, they're beautiful. They curve like this and then they curve like that because the magnetic field goes that way and then it comes back the other way. The thing, we didn't want to do that. We didn't want to do that because the more material you have out here in the detector, the less precisely you can measure what happened in the center of the detector. And that's what we want to do, is to measure what got produced in the very center where the collision happened. This is the game that we play, okay? I like to call it a game because it's always fun. Science is fun, okay? Here's how it works. Us experimentalists build this accelerator and we build a detector all the way around it. We measure, we know what goes in. We're shooting in protons. We measure what comes out. But we are not allowed in the very center. We cannot get to the very center. There's a guy named Werner Heisenberg who showed us that there's a physics law which tells us we'll never get all the way in the center there. And we cannot know collision by collision exactly what happened. We do not know that. We only know probabilistically. We know what the probability is of producing different things on the outside. We know that because we count it. We put stuff in, we have now quadrillions of collisions, so we can measure what types of things come out and how many times we see those types of things. And that gives us probabilities. We call them cross sections. The probability of an interaction happening at a specific energy between specific types of particles. So that's what we measure. We're basically just a bunch of people who count. And we have a big device like this and we count these things. And then we report these things to theorists. Theorists are really bright people. They live in the middle there. That's their life, is in the center there. Okay? And figuratively speaking. But they're figuring out, they're telling us, based on what we've measured, what are the rules? They've figured out a set of rules. And that set of rules is so beautiful, it fits on a t-shirt or a coffee cup now. And that set of rules, if you know how to use what's on the shirt and the coffee cup, allow you to predict these probabilities. But they will never let us know what happens each time there's a single collision. We can never know that. That's the beautiful thing about quantum mechanics. That's why I myself decided to go into this field. All right, let me just show you a few more things and then get to your questions. So I showed you the shaft, which goes way up there. This here is our, what we call our big wheel. We have two big wheels. They're pushed up against each other. Normally, this part here is pushed all the way back against the side here. And that magnet is pushed in. And what's on the inside there, what we call our small wheel, is pushed all the way in as well. Okay, these wheels, 1, 2, and then there's a third one behind it, are used to measure muons. Muons come out here, they're curved in the magnetic field, and we can measure by measuring their curvature, we know what their momentum is. Measuring their direction as well, we can then reconstruct what happened in the center, right? We aren't allowed in the center, but we use what came out here to reconstruct what happened in the center. So you want very little material. We built this toroidal magnet. If you have a circular magnetic field, you never have to return it. Mother Nature is happy with you. And we can make our measurements there. Now I'll tell you just the rest of what's in the detector. You can't really see it well. This small wheel, by the way, you're some of the first people to ever see it. That's our new small wheel. And if you look at atlas.cern, if you look at any of our social media, we're on everything now because we have young people working on it. So we're on Facebook and Twitter and Instagram and TikTok even. You can see videos of this being lowered down. We just installed that last week. That detector there will operate faster than the old small wheel that we had before. And that's really important because when we turn back on next year, we're going to have many, many more collisions per second. And so it's really important that when we installed that, we managed to get that ready in time, and we're going to have another one at the other end soon too. So the one last thing I can show you here. Oh yeah, well I should finish, sorry, I should finish this story. You can't really see it, but behind that small wheel is the calorimetry. The calorimetry measures the energy of everything coming out, whether it's charged or neutral. It's very dense material. It's designed to stop particles like electrons and photons and protons and neutrons, and to measure their energy. And then inside of the calorimetry is the tracking chambers I mentioned to you before that are close to the collision point that measure charged particles like electrons or muons coming out from the collision. So that's what's inside there. I can't take you in there. I'm sorry, I'd love to. There's some people working inside there now, but I can't get inside there. And then finally, I should mention, if you look at this big wheel, I mentioned that you have to do measurements to see its position. You can see some holes in parts of the detectors. That's where there are cameras used to make a measurement all the time to see its position. These sort of orange or dark yellow brown detectors here are the trigger chambers. They operate at nanosecond precision and let us know when a particle goes through and when we should take a picture. So that's how it works out here. Okay, I think I've spoken enough. Thank you for your patience. I just love our detector, so I needed to explain it to you. Maybe I can take some questions now. I'll turn this around so you can see me.
All right, so I guess we have a lot of questions in the chat box.
Great.
Yeah, so the first one, if the space is made up of dark matter mostly, can't we at Earth study the dark matter at LHC?
We hope, so dark matter, we really hope that we can see it here. It's one of our, it's one of our major goals. But we don't know. it depends if dark matter is a particle, we know it's massive because of its gravitational pull. But now, whether or not it's a particle, we don't know, but probably is a good chance that it's an elementary particle. But the trick is, can we produce it? Do we have enough energy in the LHC to produce it? If its mass is much larger than the energy of the LHC, we might not be able to produce it here. We would need a larger machine. So far, we haven't seen it, but we're going to get many, many more collisions in the coming run. The upgrade that's being done to the Large Hadron Collider. By the way, I couldn't be in here if it's during a run. We can't be in here when there's beam going through. But right now we're shut down and we're doing upgrades. There's a chance we'll be able to see that in the next run or in high luminosity LHC, which will be a run afterwards. High luminosity LHC will give us about 10 times the collisions per second. We call it luminosity than what we had in the past runs. So that might give us a chance to see it if we can produce it. If we're high enough energy, you know, E equals MC squared works 40 million times a second. We see that here. That's how many collisions we have in a second. So we add energy to these fundamental particles, which have very little mass, quarks, for example, up quarks and down quarks. That's what's in protons. We add energy to them with magnetic field, electric field. Then they collide, and that energy can become mass, a more massive particle, like the Higgs boson. E becomes MC squared, which then transforms instantly to something less massive plus energy again. So the MC squared becomes E. And that's what we're measuring there. So if we have enough E to produce the MC squared of dark matter, then we could see it. As I mentioned, because we've made a hermetic detector, a detector which completely surrounds a collision point, and you guys all know conservation of momentum means that if you project your tracks onto the plane that is perpendicular to the beams, you should see that add up to zero. When you don't, you know that something's gone through that hasn't interacted with your detector. So then we look to see whether that fits in with what's expected from neutrinos, or if it's something else. If it's at very high masses, then we will have a chance to say that we found dark matter. So we hope so.
All right, sir, that was quite interesting and insightful. So our audience has various questions that revolve around dark matter, black holes, and negative energy. So those type of conspiracies. So they wanted to know your perspective, and that particular question is, some theories suggest the formation of tiny quantum black holes, specifically through LHC. So what is your take on this, and can LHC really generate those black holes, or is it similar to any rumors or so?
Okay, so let me step back a second and explain why that will be so interesting to us. Okay, one of the forces, probably the first force that we ever understood, is gravity. Right? You see it every morning when you try to get up, and it feels really strong when you're trying to get out of bed at 6:30 in the morning. Right? That force is actually very, very weak compared to the other forces that we've measured at the microscopic level. So the strongest force that we know of is the strong nuclear force, what holds together protons, neutrons, and which holds those protons and neutrons together. Its residual force is strong enough to hold protons and neutrons together in an atom, for example. Then you have electromagnetism, which you all know, your magnet and you stick on your refrigerator, electromagnetism. Then a next weaker force, which is related to electromagnetism, is the weak nuclear force. And that gives us nuclear fission, which is pretty strong. Sun, okay? It gives fission and fusion, actually. So we have these forces that we've managed to put together in our model of particles. Gravity, however, is much weaker. I'll tell you how much weaker. I mean, you know how much weaker it is, because if you take a magnet and you go next to your refrigerator and you let go of it, the refrigerator wins. It grabs it. but you have an entire planet under your feet pulling on it with gravity, okay? The difference in strength at the nuclear level, which at the level of quarks and gluons, the difference in strength between electromagnetism and gravity is a million times. Is a huge difference. And we don't have any theory that can explain that and that can add it to our standard model. Now, some theorists said, we have an idea. What if our universe has additional spatial dimensions, or at least one? In which case, perhaps gravity is manifest in these additional dimensions, but our other forces we're only seeing here on this simple three-dimensional spatial universe that we're in, that we know of. We're mainly electromagnetic. Human beings, the forces holding us together, they're electromagnetic, okay? So we wouldn't know about them because we're on this three-dimensional manifold in a multi-dimensional space. But gravity would be in these other dimensions. And so we're only seeing perhaps a residual part of gravity, very small amount of it. That's a proposal that the theorists came up with, and these are very bright theorists, and it makes a lot of sense. But if that were true, then at the energies of the LHC, it could have been possible for us to bridge across that to that other dimension. At really high energy densities, you could see a bridging over there, and that would come in the form of a micro black hole. A micro black hole would simply be something which appears and disappears instantly and gives you a whole lot of tracks that came out, like Hawking radiation. Hawking radiation gives you a whole lot of tracks that come out. And so we look for that right away. Now, the theorists I've talked to, Lisa Randall, Raman Sundram, are brilliant, and they've already given up on it because we should have seen it right away, early on. We probably should have seen it. And so their current thoughts are that it's just not at the LHC level, we're not going to see it. And so we're unlucky. So the good part about the micro black hole, I should say, is that it got everybody excited about the LHC, because when people hear black hole, they automatically think, oh, like black holes out in space, which is really no relationship. A black hole out in space is an enormous star that's collapsed on itself and has all that mass in there, and so light doesn't escape. And that's not the case for these micro black holes we're talking about. They would disappear instantly. So sorry we haven't found them, and doesn't look like we will.
Totally agree, sir. I believe there are never-ending conspiracies related to dark matter, black holes, and negative energy out there. I believe these are the conspiracies that will remain forever. So taking the question forward, our audience have a couple of questions regarding protons and electrons that are basically used in LHC. So the question is, before these protons are accelerated, where are they specifically stored, and can we use electrons in spite of those protons?
Okay, I can tell you how the accelerator works, essentially. It's actually simpler than you think. We have a little bottle, you know, from here to here, probably. A little bottle full of hydrogen. And you just turn it on, and shooting out from that bottle of hydrogen, it's hydrogen, right? The hydrogen is simply protons with electrons. You pass that through a filter that can strip out the electrons. And once you get just the protons you can then use magnetic fields to steer them. You can chop them into these bunches I mentioned, and you can use electric fields to accelerate them to higher energies. Once they come out, they go through a linear accelerator to get them up to a certain energy. And then they actually go through history. They go through the proton synchrotron, which is one of the very first accelerators at CERN. And that accelerates them to a certain energy. And I think it's in the proton synchrotron, actually, that they chop it up into bunches. And then that gets accelerated and put into the SPS, which is what's called the super proton synchrotron. By the way, when you're naming your accelerator, don't use the word super or new, because that will get old quickly. The super proton synchrotron was the proton collider that discovered the W and Z bosons, the carriers of the weak nuclear force. And it's still active, and we use it. We use it to accelerate the protons up to a higher energy. And then we inject them into the LHC. And then again, the LHC accelerates them up, ramps them up to the energy that we need, the intensities that we need before we start doing collisions. So that's how the whole accelerator works. It's really simple. Hydrogen bottle, you just open it up. And really you could use one hydrogen bottle would take care of the LHC for its full lifetime. I think they change it every year, but you don't need to. There's plenty of protons in there. If you have a cup of coffee, you've got orders of magnitude more protons than we will ever collide in here. So that's where the protons come from. I'm not sure I remember the second question. Maybe you can remind me.
All right. So the second question was, can we use electrons in place of protons, and can we accelerate them?
That's a really, really good question. And we do that. The answer is yes. Now, and we actually have this sort of cycle that we've gone through here at CERN. So the first colliders, they use protons. Protons are higher mass. They're not fundamental. They're made up of quarks and gluons, but they're charged particles, and you can accelerate them, and they have a higher mass. So when you collide them, you can produce particles. You can go to higher energies and produce particles of a higher mass. Okay. The reason I should maybe step back and tell you why higher energy is always more exciting to us. Okay, there's two good reasons for that. One, a fundamental particle, an elementary particle that has more mass will always transform. Some call it decay. I don't like the word decay. It doesn't have the other particle in it. It's fundamental. It's an elementary particle. It's a single point. So if it's more massive, it will automatically transform into a less massive particle and energy. That just always happens. Anything that can happen, it's quantum mechanics. Anything that can happen does happen. So particles, the most massive particles, instantly transform to lighter particles. And that goes all the way down the chain until you end up with us. We're made up of up quarks and down quarks, the lightest of the particles, plus electrons, right? All the other particles, we needed accelerators, or we needed to look at cosmic rays to know that they existed. Okay, so from the beginning of time, instantly all the more massive things disappeared. So that's why we're interested in reproducing them, to measure them. Another way to look at it is there's a brilliant equation made by Planck called E equals h nu. Okay, h is just a constant, Planck's constant, but nu is the frequency. Okay, frequency goes 1 over the wavelength. Okay, so the energy is inversely proportional to the wavelength. So if you want to probe the smallest parts of nature, you need to go to higher and higher energy. So there are two ways to look at the fact of why we want higher energy and how we use it to try to understand new things. Now, the way we've done it here is sometimes we have proton accelerators because you got the higher energies because it's a more massive particle. And it allows you to explore, because when there's a collision of two protons, you cover a whole range of different collision energies. You're at different collision energies because you don't know which quarks are going to run into each other and what they're doing, because the quarks are moving around all over the place before they collide. Okay, so you get a range of energies of the collision, and so you can scan and look for new things. So discovery is often done with protons. Electrons are awesome because they're fundamental particles. And so when they collide, you can tune the energy at which they collide exactly. So as an example, the accelerator I worked on when I first came over here was LEP, the Large Electron-Positron Collider. We collided electrons and positrons, their counterpart, their antimatter part. That is even more collisions, okay? So we did that because we wanted to measure a particle we had discovered previously with a proton collider called the Z boson or Z boson, and the W boson as well. But the Z boson we could produce with electrons and positrons, because the Z boson will transform to electrons and positrons. So we ran the accelerator at exactly the mass of the Z boson, and then you get a big peak. You produce a whole lot of them. A whole lot of Z bosons will get produced. Then you can measure them precisely. We're doing the same thing here for Higgs bosons. We're producing a lot of them in order to measure their properties precisely. And now it turns out with electrons and positrons, you can do very, very precise physics, but you're not going to produce as many Higgs bosons unless you have a really, really high energy machine. It's not so easy to produce that machine. We are looking into that. There's a group of people called the International Linear Collider. It's a consortium who are interested in producing a machine that hits electrons and positrons at very high energies to produce Higgs bosons and anything else that we discover here. And that would probably, Japan is probably the candidate to have that. CERN was interested as well. And then we'll also look at producing, when we make a new ring, so we're very much interested. We do a planning session every 7 years or so. We all get together and we write these papers trying to understand what's the best way to do new physics. And one of the plans is to build a very, very large ring, probably 100 kilometers around here at CERN, which could first collide electrons, just like you asked. Very good question. Collide electrons to precisely produce tremendous numbers of Higgs bosons or other particles, and then move on to protons so we can do more discovery. So we sort of do these sort of, you know, first a proton machine, then an electron machine to clean up and do the precision physics, and then back to protons for discovery. But we're finding with the LHC, we don't just do discovery, we can do precision physics because there's so much data. And so that's what we're doing here. There's a long answer to you, but I hope that explains protons and electrons.
Yeah, that was an amazing explanation for that answer. And as we said that the questions about, you know, negative energy cannot come to an end. So one more on the same. What is the actual meaning of negative energy? How do we define it? Or, you know, where do we find the negative energy or negative energy holes?
So I'm a scientist. I will say right away, I don't know. I don't understand negative energy. I'm not sure I understand the context of the question, because I mean, there's certain strange things that you can do with quantum mechanics, like for a very short instant of time, I suppose you could have negative energy, but it's really not something that, you know, that in real life you're going to see. Okay, so I'm not sure I understand it, or maybe you need a theorist to really discuss this in more detail with you. Sorry.
Okay, all right, no issues, sir. So let us move to the next question. So you guys are continuously working day and night at the heart of the place where physics research takes place, that is CERN. So you guys must be facing some technical challenges as well when you work on microscopic scales. So if you would like to reflect some light on that aspect regarding what basic technical challenges you guys face at CERN, any of comment on same?
There are many challenges. You're absolutely right. Every aspect of building an experiment like this, you know, human beings, we survived millions of years, I would say, as we evolved using one beautiful instrument to make precise measurements. There's an instrument that we have that can resolve to tens of microns, and which can see millions of light years away. And that's this, it's the human eye. It's an incredible instrument. So don't, you know, and then you got hardware attached to it with software on the inside. It's fantastic detector, but it's got limits. And so over time, we've developed other devices to allow us to make measurements of the parts of the world that we couldn't see with the eye. I once had one of these virtual visits, and there was a young student, probably 13, 14 years old, maybe even younger, in Alaska. And he turned to me and he said, "How do you measure what you can't see?" And that question has stuck with me ever since, because that's what science is. That's what we're trying to do here. That's what we're trying to do everywhere. Exploration is measuring what you can't see. That's why we built ships and traveled around the globe to see things we couldn't see. And that's why Galileo and Newton and all built telescopes so we could see further out into space. And then we also built microscopes so we could see deeper into nature. And this thing here is just a microscope. It's just a very powerful microscope. We use protons instead of light, but that's all it is. It's like a lens, and you're looking at nature as closely as you possibly can. So we want to push it as far as we can. We want to see as much as we can. So you have to build detectors. I mean, from the inside out, you have these silicon detectors. You want them to be as precise as possible. So you need to have chips in there. You need to have silicon that can measure to as few microns as possible without giving sort of electronic feedback between different channels. So we push that to the limits. And after we're done with our design and we work with engineers to make the design, and we go to a company and say, you got to produce this, they always say, there's no way. And then we have to work with them and come up with a way to produce those things that we need to make the measurements we need. So we push in the detector components. Outside of that, you have scintillators and which you want to be as fast as possible, which won't age when they get hit by beam all the time. So scintillator is really cool. It's a sort of plastic that has different materials inside it, which when a particle comes through, they give you light. They tell you, hey, something came through here, and the amount of light tells you the energy of the particle that went through. And so we have that on the inside to do the calorimetry on the inside here. So you have challenges that everything has to be radiation hard. We test everything. We bombard stuff. We got an example of the electronics or an example of the detector, and we test it by irradiating it. We see what happens over time. Some of the new stuff to go inside here. I've had students, I oversee student programs where undergraduate students come here, and they've been trying to understand some different things with a specific chip. After it gets bombarded with radiation, it operates differently. And so they have to understand that, and they have to improve it. So there's these technical challenges. And you have taking the data, the electronics. How do you take data at such a high rate? How do you do it without overlap between events? When there's a collision in here, there are many particles in a bunch. So it says 100 billion. And if you get a certain number of collisions, say 60 that happen, you got to figure out where your particles came from, which collision. And so you need to work that out both by having very fast detector and electronics, and also very good software that can work out which tracks came from which collision point. Software challenges are phenomenal. And we're always pushing that, because we're also physicists who get our hands into everything. Physicists want to do everything, and we do, and we write the code. And perhaps sometimes it's not the best, but we want to solve problems that others have never solved before. The magnetic field, we said, okay, let's make a toroid instead of a solenoid, because then we can have less material on the inside, and we can measure the muons out here more precisely. But that requires mapping the magnetic field. If you have a solenoid, it's a uniform field. If you have this, it's an incredibly complex field. It can be very strong at certain parts and very weak at others. You need to have a precise map of that in order for you to figure out what the momentum is of the particles that came through. So and then how do you get the computing power for that? We can't do that just at CERN. We do the first processing here at CERN across the street, and then we ship the data to different data centers all around the world. There's about a dozen different data centers around the world, which then take that data and they process it. I'm going to move here so some people can come through. And they process it, and then they ship it on to other locations, which then allow us physicists to submit jobs to get processed. So we send our computing jobs to wherever the data is. So we had to solve that problem. We did that by making the computing grid. Earlier on, before the LHC, when we were working on LEP, we had this problem, simple problem. How do we communicate with each other? We're producing vast amounts of papers, of information, of knowledge, human knowledge, and we want to share it with everyone as quickly as we possibly can. What's an effective way to do that? We had this thing called the internet. And so a guy named Tim Berners-Lee, who was working here at CERN, said, well, you know what, we know what hypertext is. We could make a program which allows you to share these and simply use these new devices called mice to click on different words and go to another place. And so he invented the World Wide Web, which allowed us to share all of our knowledge more easily. And you know, that's a quite promising invention. So all of these things, the challenges here are immense. I haven't even touched on the fact that you have the LHC running at 1.9 Kelvin, colder than the universe. You have to create that in order to use niobium titanium at a temperature where it's superconducting. So you can have very powerful currents to give you the strong magnetic fields that you need. That happens in the accelerator and also inside our magnet as well. We use niobium titanium. So, I mean, I just touched on some of the challenges for the LHC, but there are many, many more. I'm going to take you for a walk. You can ask me more questions. We'll go for a little walk and I go to the other side so you can see the other side.
All right, sir. Our chat box is totally flooded with the question, I must say. And like people are really interested in knowing more and more what is happening at CERN, basically.
Uh-huh.
All right. So let us move. Yeah, sir.
All right.
What was you going to say? Is that a general question, what's happening at CERN, or did you have more specific one?
All right, sir. So people are specific as well. So let us take the next question. Yeah, Tanisha, you can.
Okay.
First.
All right. So the next question, we start speculating the possible results of an experiment using our standard model. So at what point in experiment do we realize that there is some quantum mechanical discrepancy coming into the play?
Okay, that's great. That touches exactly on what we're trying to do here. Let me just show you, give you the opportunity while you're here to show you, we're at the other end of the detector. This is what's the old small wheel. We hope that we're going to be able to lift that out and bring in a new one here in a couple of months. We're working on that so that we're ready to take much more data. Taking much more data is the way we go about trying to find out what's wrong with our standard model. So you're correct in saying, you know, that we're looking for discrepancies. Physicists, scientists, we're all interested in things which disagree with our current theories. So in that sense, we're the opposite of, say, a politician. I love politicians, don't get me wrong, but a politician will simply have a policy, and when they're talking to the public, will just look for information, data, which backs up what they're saying and ignore anything that contradicts it, okay? Unless they're really good. If they're really good, they will listen to scientists, they will look at the real world, and they'll say, hey, what's going on is not what we thought it was, and so we're going to change our minds. So please, when you vote, and you have the biggest democracy in the world, be patient. And a politician who's willing to change their mind because they've got new data is a good one. And that's what we do here. We have a problem. We're missing 95% of the universe in our current model. It's missing a lot of stuff. And gravity is not in it either. So there's a lot of stuff missing. So we know it's got a problem. The thing is that every single thing we've measured so far here in the LHC has only confirmed it to higher and higher precision, which, you know, it's great. On one hand, just shows what a brilliant theory it was that got put together. The guys who, you know, one of the founders of this, Weinberg, just died a few days back. One of the brilliant physicists who came up with electroweak theory and the standard model. It's been brilliant. It's predicted many, many things. And we operate at higher and higher precision, higher energies, but more importantly, higher luminosity to get many, many more collisions, much more data, so that we have smaller and smaller error bars, right? These are the things that, unfortunately, the general public doesn't always understand these. You guys do, and it's important. I do a lot of science education. It's important to understand the error bars. This is what we spend almost all of our job working on. To measure the mass of the Higgs boson, it's one line of code. You can calculate it. You put in the momenta of the tracks, their angles, and boop, out pops the mass. The most important thing to get from there is how well do you know that mass? What is the uncertainty of it? And for that, you need to study your systematics. How well can you make a measurement? You know, how well did you measure the momentum of each of those tracks? How does that propagate into the calculation of the mass? But also to make the measurement many, many, many times, because there's statistical uncertainty and systematic uncertainty. For the standard model properties, and such as the Higgs boson that's a part of the standard model, we have predictions and we compare what we measure with the predictions. Really good example, a good friend of mine, Mohammed Al-Rub, who helped to organize our virtual visits here. He's in charge of virtual visits. He was one of the chief people investigating a measurement which might sound peculiar to you, is looking for collisions that produce 3 W bosons. And they just recently released it. It's a discovery because it's the first real observation. I mean, it was predicted by the standard model, but to observe it means you need to have at least 5 standard deviations above what would exist if it didn't exist. So you might see a peak in a distribution. It has to have more than 5 sigma, like the Higgs boson, for you to be able to say that, yeah, you've seen it. There's evidence. It's clear. There is something there. They got 8 sigma. Very, very clear measurement, beautiful work. And it was done using precision, hard work of trying to beat down any of the errors that were there. In many cases, we have to use, in computing, we have to push machine learning, for example. We had to learn how to use that in an effective manner, and use whatever techniques we possibly can. So we're measuring everything that's predicted by the standard model, every possible thing. Another really good example is the measurements of the Higgs boson transforming to other particles. So we could discover it early on because it transforms to the more massive particles first. So when it transformed to 2 Z bosons, and those transformed then to electrons or muons, we could put those together and we could see the signal very clearly. But if you go to something which is less massive, then you're not going to see it. The probability of producing it is smaller. And that makes sense, right? Because the Higgs field is the reason that fundamental particles have mass. A mass of a particle is a measure of how much it interacts with the Higgs field. Much like if you have a charged particle, it interacts with an electromagnetic field, and the more charge it has, the more it interacts. It's a similar thing. Okay, so mass works that way. Therefore, when a Higgs boson transforms to other particles, it will transform more to the more massive ones than the less massive ones. So we have measured the Higgs boson interacting with top quarks, with bottom quarks. We've seen it interacting with Z bosons, W bosons. And more recently, we've started perhaps to see it interacting with muons and charmed quarks, but they're much less massive. So we need much more data. So to be able to measure these things, we need higher rates, and that's why the LHC is being upgraded. So that's how we sort of check things. More data, and we'll upgrade again in about 5 or 6 years to even more data per second, so that we can look for these really, really rare phenomena. And of course, as I said, our hope is always that we see a difference between what's predicted by the standard model and what we actually measure. And that will give us a hint on where the new physics is. But it hasn't happened yet. We're still looking for that.
Sir, that was really a very detailed answer. Thanks a lot for elaborating many different dimensions to that particular answer. So moving to our last answer for the day, and this was a common question from all of our audience. How far your experience has been into CERN, and what is your source of motivation, or let's say, what do you recommend to our future scientists or future engineers who are taking or who are looking forward to make a career, and how to enter into CERN specifically? So any of your guidance on this aspect?
Okay. That's full of great stuff in that question, but I love it. It's a, first of all, I have to admit, I'm really lucky. This is a fantastic place to work. I get to work with people from every corner of the globe. The globe shouldn't have corners. From every part of the world, let's say. And they're people with different social backgrounds and cultural backgrounds and linguistic backgrounds and everything, culinary backgrounds, every possible background. That's important for science, right? Because when you're trying to solve really complex problems, it's important that you look at it from many different points of view. So it's not just being lucky that people come from different areas, or that we need them because we need resources to be able to produce something like this. It's also extremely valued. Diversity is extremely valuable. It's valuable for our species, and it's valuable for us to do science. Okay, so that's one of the great things about being here. Now, let me tell you how CERN works. CERN's a laboratory. There's roughly 2,500, 2,600 or something people who work for the laboratory. Most of those people are support staff. There can be administrators. And there are some engineers, technicians, and very, very few physicists. Okay, so working for CERN, there are dozens, I'd say, of physicists, not many. They embed themselves on some of the experiments and also help to work on the accelerator and other things. Now, most of the people here are like me. We aren't on the CERN payroll. We don't get checks with CERN on it. They get it from our institutes. There's about 14,000 of us who are called users. And that's how most people make it to CERN. I came here as a graduate student from the University of Michigan. I worked for them for some time. Then I moved over and worked for Northeastern University. Then I worked for University of Lausanne for a significant amount of time, finished up LEP on there. Came back to the University of Michigan when the LHC started up. And then I'm working for the University of Melbourne most recently, for quite some time now, actually. And it's great to have these different people who we get to work with, but that's how it works with a user. Most of the users, they could be faculty. Many of them are senior faculty, so they don't get to come here very often. They have to work remotely from home. We know that works now because for the past year and a half, we've all been working remotely from home. There's been a very few people here who were able to come in and actually work physically on the LHC, and they had to do it with masks. They had to do it very carefully. It's been very hard to catch up, and the turn on of the LHC has been delayed a little bit because of that, but that's normal. I think the world got delayed by a little bit. So these people, we all come from different institutions who are members of experiments. The University of Melbourne participates on the Atlas experiment. So if you're young and you're saying, I would like to pursue a career as an engineer or a physicist working on one of these experiments, then what you need to do is to find a university or a laboratory near you that is working on it. Now, India is a member of CMS, a very, very active member of CMS. There are a lot of good work being done over there. So if I were in India and I was thinking I wanted to do this, I would probably check the major institutions. You can simply go to, say, the CMS web pages, and you can probably find out from there easily what institutes are members. And then you can consider applying to one of those institutes for school, for your studies. You have to be loud. You have to go to the institute and say, hey, I'm here. I understand that you're a professor who's working on CMS. I want to help. How can I do that? I want to become a physicist who works on CMS. So be sure to do that. Be sure to look into it, find out who's doing it, who are the scientists who are involved, and give it a try. Yeah, that's the right URL, but there's another URL that's even easier. You can go to cms.cern, cms.cern, just like atlas.cern. We all got this new URL, which will go directly to our pages. So I have a lot of good friends on CMS. They do really, really good work. So I would look for that. You can look at the other experiments too. I don't know if India is a member of other experiments, so take a look around to see. Or maybe you want to go somewhere else to go to school. You don't have to stay in India, right? There's a whole world out there of universities and laboratories where you could go to do your degree. Undergraduates can get involved. Graduate students, for sure. As an undergraduate, I studied mathematics. I actually went in to become a doctor, and I changed my mind to math, and then I changed my mind again to physics at the very end, and did my PhD in physics. And when I was doing that, I hadn't even thought about what I was going to do in physics, but I got a phone call because they needed someone to come over here to help work on a detector for a summer. And I said, yeah, sure, I'll go to Switzerland. Sounds great. And I've loved it and stayed ever since. So that's the main way to get into it. And as I said, note it's not just physicists. If you're an engineer, you can work on this. There's technicians who work on it, but you have to find an institute that's involved in one of the experiments. And then there's not just the LHC. You don't just have to come to CERN. There's other really good physics going on all around the world. Maybe you want to work on Ice Cube down at the South Pole. Not many people go down there, but maybe you want to work on any of the new experiments like DUNE, which is a neutrino experiment in the US being built. Fermilab, Japan. There's many, many places where it's going on. It's a fantastic field because you get to travel to many of these different places and to work on things. So I encourage you to do it and give it a try. And I hope to see you over here. Come find me when you come over.
Thanks a lot, sir. Thanks a lot. Yeah. I was
going to say, I'm not sure if I answered all aspects of the question, but
yeah, definitely. It was a full pack answer, sir, a fully packed answer. I hope the audience has get a perspective on how to get into CERN. So, sir, there are many other questions as well. If you can like provide your email ID or any contact details, like how can our audience reach out to you or through LinkedIn, basically?
So you can always find me. They have my name. I'm on social media everywhere. I have to admit, I don't do TikTok a lot. I'm a little too old for that. My thumbs are a little too big. But you can also find, I would highly suggest interacting with Atlas in general. Atlas has very active on social media. They have younger people than me running it. We're on Facebook and Twitter and Instagram and TikTok, as I mentioned before. You can see a lot of things there, and you can always send us questions. I maintain the public web pages, and at the bottom of the public web pages, you can always contact us. Not many people do that. It's usually meant just for feedback, but you could always do that as well. But you can find me if you put my name anywhere. My son teases me because if you search my name, you find my entry on IMDb, because I was for 10 seconds in a film once. or I was on 60 Minutes for an interview once. And so that shows up first, but you can find me in different places.
That was really nice, sir. So I hope our audience has get an answer to how to connect with sir. So I request Akriti to please take over for further proceedings. Over to you, Akriti.
Thank Thank you so much, sir, for your valuable time as well as for this insightful session. I hope all the participants enjoyed it as well as learned something new and interesting from this event. Now, I would like to request Rashmi ma'am to add ending remarks to the session and present the virtual memento to Dr. Stephen Goldfarb. Ma'am, please.
Okay, hello everyone. So how was the event? I think fabulous. So I think it was fabulous seminar which turned out to be great successful. All the queries were solved so patiently and so elaborately. I'm really surprised you have given so much time to our students. I'm really thankful that you have spared so much time for our students, for us, for all the participants who are participating today. So I'm here to present a vote of thanks to the people who made this event thriving. I will really take just a minute to thank all of them. First, I would like to thank Dr. Stephen, who shared their fastidious expertise with all of us. Your explanation was astute and thankful. So please accept this virtual memento presented to you by our team as an earnest symbol of gratitude. Sir, this event would not have been successful without our esteemed speaker, the students on the organizing committee, and our lovely audience. So thank you very much for paying your valuable attention and also suggesting your opinion. We are very thankful to you, sir. So please accept this memento from our organizing committee side.
Thank you very much. Thank you
Thank
very.
you.
I really appreciate it. It was fantastic. All of the questions.
Yeah, it was really a very great experience. I think this is a experience which we people are facing for the first time. So just see the participants. There's so many participants on YouTube, on this channel. Everybody wants to attend this virtual tour. Thanks a lot, sir. Thank you very much.
Okay, thank you. I hope to see you next year. Let's do this
Yeah,
again.
so it will be pleasure for us to see you again. Yeah, thank you very much.
Okay, thank you.
All
Bye,
right.
everybody. Oops, go
Yeah,
ahead.
just a minute, sir. Just a minute.
Okay.
I would like to request every participant to switch on their camera for capturing this wonderful memory.
All right. I request everyone to kindly switch on their camera. All right. So let us take a screenshot on the count of three. 1, 2, 3. Cheese. Perfect. Perfect.
You can't see, but I was smiling, just so you know.
All right. So yeah, thank you so much, everyone. It was great having you all. Special thanks to Steven, sir. And we do really have great audience on YouTube as well. Almost 70 to 80 people were there on YouTube, and almost 100 people were there on Zoom link. So that was really a wonderful experience listening to you, sir, and listening to your experiences. We really look forward to host you in the near future as well. Thank you so much, sir.
Very
Thank you.
good. Okay,
Thank you,
thank
sir.
you. I'm very happy you've been a part of this.
Thank you.
Thank you so much.
Thank you,
Goodbye,
everyone.
everybody. Take care. I hope to see you again soon.
Bye-bye, sir. Take care. Thank you so much.
Bye-bye.
In the end, I would like to extend my heartfelt gratitude to every participant for making this event a great success. Hope you all enjoyed and learned something valuable from it. This was an amazing event that owes a majority of its success to the enthusiasm and participation shown by all the students who joined us for the events. Thank you to everyone, and we wish to see you soon at another event of ours. Thank you so much.
I think we should give a big clap to everybody, the whole organizing committee. Keep it up, keep it up.
Thank you so much, ma'am. All right. Thank you so much, participants. It was great having you all. Hope it was a great learning experience for all of you. So you guys can take a leave for the day. Thank you so much. Bye-bye. Take care.
Yeah, I would like to mention something. I believe there are some international participants as well. So a big thanks to them. Yeah, you guys just made our event successful. Thanks a lot. Thanks.
Thank you very much. Thanks. Yeah, you make our event a successful event after your participation. Thank you very much. We will need your participation in other events also. Thank you very much. Tanisha, you have taken the photograph?
Yes, ma'am, it's done. Yeah.
Thank you, ma'am. Thanks a lot. You are from which place?
Thank you.
Yeah.
From Nigeria.
Yeah.
Nigeria.
All right.
Nigeria.
All right.
Wow, wow, that's great. So how do you like the event? Please give us a feedback.
Oh, okay. I'm going to do that. Yes.
Okay.
I'm more of electrical electronics, and I really enjoyed the physics part of the event, and the tour was really great. Yes, I loved it.
Thank you
Thank
very
you very
much.
much.
Thank you. You're also
Thank you so
engineer?
Yes, yes.
Okay. Thank you.
All right.
Thank
Thank you so much, ma'am. Thank you so much for being a part of our family of this particular event. Thank you so much, ma'am.
you.
Yes. Yeah.